In this video, we cover a big list of examples where we're trying to evaluate a limit, but the limit approaches the indeterminate form 0 divided by 0. So basically, all the most important limits in Calculus 1 suffer from this problem. So we're going to develop a small set of algebraic tools allowing us to get a clear answer when we run into a 0 over 0 type of limit. Now, I do want to point out that the last problem is a little bit different. In the last problem, the denominator vanishes, and we have to deal with that, but the numerator is not approaching 0. And this just seemed like the best place to fit in that sort of example, so we'll look at that toward the end of the video. So we've got 6 examples ready to go with vanishing denominators in the limit, and let's get started. Our first limit is the limit of x squared minus 16 over x minus 4 as x goes to 4. So we just check really quickly. If I replace x with 4 in the denominator, I've got a problem. It's a 0 down there. I also noticed that replacing x with 4 in the numerator gives me a 0. So we've arrived at this indeterminate form of 0 over 0. Now what occurs to me in this example is that we might factor the numerator. And I recognize that as a difference of 2 squares. This is x squared minus 4 squared. So that's going to factor into x plus 4 times x minus 4. And things are working out really nicely here because now we have a common factor that's going to cancel out. So our limit reduces to the limit as x goes to 4 of x plus 4. And that's just the limit of a simple polynomial function. And replacing x with 4 doesn't cause any more problems. So this limit unambiguously goes to 8. In our next example, we have a limit as h goes to 0 of 1 plus h quantity squared minus 1 divided by h. So we see immediately that the denominator is vanishing here. And if we replace h with 0 in the numerator, that would give us 1 squared minus 1, which is also 0. So we've arrived at our classic indeterminate form, 0 over 0. And we have to start manipulating this until we get something that's less ambiguous. So in this case, what I'm going to do is expand that numerator. I have a squared binomial in there. And I'm thinking if I go ahead and expand that, maybe we can find some simplifications. And I want to take the time to point this out because it's a really common mistake. 1 plus h all squared is saying multiply 1 plus h by itself. It doesn't mean you just square the first and last terms in there. There's a cross term that appears when you multiply binomials. So we'll go ahead and write an intermediate step like that. So when I expand that binomial, I have to take every possible product containing one term from each binomial. And we normally just summarize that with the acronym FOIL for first, outside, inside, last. So when I do this expansion, I start with a 1, just multiplying the 1 and the 1. And then I get 2 cross terms. Each one of those is a 1 times h. So that gives me 2 h's. So I have 1 plus 2h. And then finally I get h times h, which is a plus h squared. So then a really nice thing happens. I have a 1 out in front and a negative 1 at the end up there in the numerator. And I realize my leftover numerator is factorable. I can factor an h out of this guy. Now that I have that h factored out, I find a common factor to cancel, and that problematic denominator cancels out. This leaves me with the limit as h goes to 0 of 2 plus h. And now this is the limit again of a simple polynomial function, and I can just replace h with 0, and this limit goes to 2. In the next example, we have a problematic denominator that involves a square root. So we're told in this example, we're taking the limit as t goes to 9 from the right. The reason we had to specify that is because this square root function is not going to give us a real result if t is less than 9. So we're taking the limit as t goes to 9, but only for values of t that are slightly bigger than 9. And I notice if I do a direct substitution here, I end up with a 0 over 0 indeterminate form again. So there is a way to just simplify this expression. If you notice that the numerator is just the value of this variable expression, t minus 9, and then the denominator is the square root of the same thing. So anytime you have a variable, I'm just going to call it x for a second. Anytime you have a variable divided by the square root of the same thing, that's going to simplify to just the square root of that variable. So that's the basic motivation behind our plan, but we can show some algebraic steps as we modify this limit. So what I'm going to do is just multiply the numerator and denominator by that square root of t minus 9. And if you like, you could say what we're doing here is just rationalizing the denominator and hoping for the best. So now the numerator is still pretty messy. It's t minus 9 multiplied by the square root of t minus 9. But the point of this manipulation is that the denominator now just becomes t minus 9. When I square a square root, it undoes it. And we're in luck, seeing that a factor of t minus 9 is going to cancel out here. And we end up with the limit as t goes to 9 from the right of the square root of t minus 9. Now replacing t with 9 doesn't cause any problems to occur, and I end up with the square root of 9 minus 9, which is 0. In our next example, we have another limit as h goes to 0, but this time we have a complex fraction. So in the numerator, I have 1 over a plus h, where a is just some constant, minus 1 over a. And notice that that numerator goes to 0 if I replace h with 0. And then in the denominator for this whole thing, I have an h, which also goes to 0. So again, we land on this 0 over 0 indeterminate form. Now, when we see a complex fraction, the first instinct here is to just combine this all into a single fraction and hope for the best. So what I'm going to do is get a common denominator up there in the numerator of this complex fraction, and that means multiplying the first one by a over a. So I end up with an a, and then in the denominator, I have an a times the quantity a plus h. In my second fraction, I'm going to multiply that by a plus h over a plus h. So the numerator is now a plus h. And my common denominator, again, is a times a plus h. And our original denominator for the whole thing is still h. So with that common denominator, I'm able to go ahead and do the fraction subtraction up there in the numerator. So I have an a minus the quantity a plus h, then divided by a times a plus h. And I still have that h hanging out in the denominator for the whole thing. So in this step, we'll do a couple things at once. I notice that I have an a minus a when I distribute that minus sign, and I'm left with a negative h in that numerator. Secondly, dividing this complex fraction by h just puts a factor of h into the denominator of that fraction that was on top. So I end up with an ha times the quantity a plus h. Now at this point, our h's are going to cancel out, and I end up with a negative 1 in my numerator and an a times the quantity a plus h in the denominator. And now I'm looking at a rational expression where directly substituting in h equals 0 doesn't cause a problem. So this thing finally simplifies to negative 1 over a squared. In our next example, we have the limit as x goes to negative 3 of the square root of x plus 4 minus 1 in the numerator, and then an x plus 3 in the denominator. And we notice that direct substitution, putting in negative 3 for x, is going to give us a 0 over 0 indeterminate form again. Now there's a common trick for this type of expression where I have a square root of a thing plus or minus a constant. And the trick is to multiply by the conjugate. And when we multiply by the conjugate, what we're doing is intentionally building a difference of two squares. So I'm going to take the same expression, but change the sign in between the two terms. If it's a minus, change it to a plus, and vice versa. Now that numerator is going to become a difference of two squares, but I still have to do the same operation to the denominator. And when I multiply all the terms in that numerator, I have the square root of x plus 4 multiplied by itself. That's going to give me just an x plus 4. That's the whole benefit of doing this, is that we're building a difference of two squares, and squaring undoes the square root. Now the cross terms, by design, are going to cancel. I have a plus square root x plus 4 and a minus square root x plus 4, so those are gone. And then I have a minus 1. Left over in my denominator, I have the quantity x plus 3 multiplied by the square root of x plus 4 plus 1. So our numerator has simplified to x plus 3, and I have another x plus 3 in the denominator, and this is the moment where we realize that our problematic factor is going to cancel out. And we're also carrying another factor in our denominator, square root x plus 4 plus 1. So the x plus 3's cancel out. That leaves us with a factor of 1 in the numerator. And now if I check the idea of directly substituting negative 3 for x in this denominator, that just gives me a square root of 1 plus 1, which is 2. So my numerator is 1, my denominator is 2, and we've got the value of our limit at 1/2. Now I pointed out in the introduction that our final example is a little bit different. We're taking the limit as x goes to negative 2 from the left of this giant rational expression, 2x squared plus 7x minus 4, divided by x squared plus x minus 2. And if I play around with the idea of directly substituting x, you can do that provided it doesn't create a vanishing denominator. But when I replace x with negative 2 in my denominator, I end up with a 4 for the first term, minus 2 minus 2. That's 0, and that's a problem. However, this isn't a 0 over 0 indeterminate form, because if I replace x with negative 2 in my numerator, that's going to give me a 2 times negative 2 squared plus 7 times negative 2, which is negative 14, minus 4. So this first piece is 8, and I have 8 minus 14 minus 4. That's not 0. So I think the best first step here is just factor everything and see what we're left with, and then we'll talk about how to deal with it. So factoring the numerator, I don't have a coefficient of 1 on x squared here, so my guess and check game gets a little bit harder. I know if this factors into two binomials, they would have to start with 2x and x, respectively. I know my constants have to multiply to negative 4, and then I just play around with what those constants have to be until the cross term works out. Now it looks to me like a plus 4 in my second binomial is going to be promising because that would give me a term that's 8x. And then if I put a minus 1 in the first binomial, I get a minus x. That gives me my 7x. And just to check that the constant works out at the end, negative 1 times 4 is negative 4. So there's our factorization. Now in the denominator, it's a little bit easier because my coefficient is 1 on the quadratic term. So my two binomials simply start with x's. I want the cross term to come out to positive x, so I'm going to put a plus 2 on one of those. That would give me a 2x in the cross term, and then a minus 1 on the other. Now my cross terms are 2x minus x, which is just x. And my constant, just as a final check, is negative 1 times 2, which is negative 2. So unfortunately, nothing is going to cancel out here. But I have managed to highlight the problematic factor in my denominator. That's the x plus 2, because that's the part that goes to 0 when I replace x with negative 2. So what we're going to do here is use the limit laws to split off the problematic factor. The limit of a product is the product of the limits, so I can rewrite this as the limit as x goes to negative 2 from the left of this problematic factor, that's a 1 over x plus 2, multiplied by the limit of all the other stuff. The limit as x goes to negative 2 from the left of 2x minus 1 times x plus 4 over x minus 1. So now this second piece is just the limit of a rational function, and I can evaluate that by direct substitution. And then the first piece we've discussed previously gives us a spike to infinity or negative infinity, depending on the sign of that denominator. So we'll deal with our infinite term first. I have the limit as x goes to negative 2 from the left. So that means I have a denominator that's approaching 0, but the x values I'm subbing in there are less than negative 2, which means the denominator is always negative as I approach 0. So as that denominator gets closer and closer to 0, 1 divided by that denominator gets larger and larger without bound, in other words, infinite. But the denominator is negative, so I'm spiking to negative infinity. Now in this other limit, I just get some finite number out of it. But I need to know whether or not it's a positive number or a negative number. So I'm going to do the substitution replacing x with negative 2. So in my first factor here, replacing x with negative 2, that gives me a negative 4 minus 1, which is negative 5. In my second term, replacing x with negative 2, that gives me a 2. And then in my denominator, replacing x with negative 2 gives me a negative 3. So that's a negative divided by a negative, which gives me a positive result. I could write one more step here to simplify things. This is negative infinity times 10 thirds. And that gives me a negative infinite result, so I have negative infinity as the value of that limit. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.